the last time, let's review what happened in the last time. So we motivated ourselves why we should be looking at problems to solve underlying problems that are inherent in standard model. Am I audible at the back? Not that much? Better? Okay. So we motivated ourselves why we should be going beyond the standard model and the problems that we see arising from standard model inherently or yeah. And the ways to go beyond this is to consider more symmetry or extra dimensions. So more symmetry, I think a brief analog was given yesterday and in the beyond the standard model class. But the next one, the one that remained, is the KK compactification. I'll revisit this very quickly because I feel we need to understand this because we will be dealing with compactification a bit in the main school in good capacity. So I gave a simple explanation. You have a scalar field in 5 dimensions where one of the extra dimension is that of a circle. So if this points, if I think you know this, if you're on a circle, if you come back 2 pi r, you return to the same point. So since the extra dimension is periodic, that after 2 pi, you come back to the same point, you can do something that we always do when we see periodicity, Fourier expansion. So by doing that, and just by plugging this here, what do we see? We see that a free scalar field. Is this a highlighter? What is a highlighter here? This one? Okay, yeah, let's see. Just by this was a free scalar field, like a vanilla free scalar field. But this, in 4 dimension, a 4-dimensional observer would perceive this as this. How are we pulling this off? Because of this. When your derivative hits this, you're pulling in n over r once and then n over r twice. And if we remember our Klein-Gordon equation, which was right, I can identify this in 4 dimension with this, or this is actually this. There's no actuation going on. So this is 4-dimensional scalar field just from one extra dimension gets a mass in 4 dimensions. That's weird, right? A 5-dimensional free scalar field gets mass. So in 4D, you get a massless scalar because if n is 0, you don't have a mass, plus a bunch of massive states. That is a bunch of massive scalar fields. These massive states of this, okay, I should be clear. This is the same scalar field, but getting a mass at different scales of energy. So these masses are separated by 1 over r, 2 over r, 3 over r, because n can be 1, 2, 3, and so on. These are separate fields. These are called the Kaluza-Klein tower or momentum states because they are arising from momentum in the extra dimension. So if you look at the exponential term, that is where they're coming, how we're pulling this off. We're taking the derivative, which is hitting the exponential term, pulling out n over r, and you have n squared over r squared, the mass states. Yes. Exactly. And this is a very important question because one of the questions, I didn't want to get into this. This is a very interesting question. They have the U1 symmetry, yes. But not always this Kaluza-Klein compactification have this group symmetry. When you have this, when you have this, okay, yeah, this is a more, I should not, this is a very complicated question. So this is called consistent truncation. Not always you cannot neglect that. It turns out in physics, not always you can neglect the higher dimensional mode. I'll confuse people. I'll tell you at the end of the class because this is a bit, just remind me the word consistent truncation. Okay. Okay. So I'll just from a scalar in 5 dimension, we get a scalar field in 4 dimension with this mass, and they're separated. So as we know, energy scale can be identified with the mass scale. As we move in energy by this discrete amount, your field gets a mass by the same amount. Let's say we are here. Let's say we live here. Let's say we live here. Let's say we build a very strong collider and move to this energy state. This moving or getting to that energy scale will automatically in the collider show us that our scalar field that we saw is massless is now massive. And this is an observable effect. So this is a toy model that I'm considering. This is not the universe we live in, surely. This is a toy model that I'm trying to consider to build our intuition. Mass. And then if we move the same amount, let's say this is 1 mkk, this is 2 mkk. When we move to that scale where mkk I'm saying is 1 over lkk or 1 over r. If we move to the second energy scale by this amount, make our colliders more powerful, but by the same exact amount, at this scale, we'll see that the scalar field has twice the mass it actually had at the energy level here, because energy is mass. All right, let's write it like this. Is this clear, or I made people more confused? Somewhat? Somewhat? Okay. Okay, so we can play around this again. So we can do this for a gauge field in 5 dimension, play around, and the punchline that I wanted to give is 4-dimensional gauge fields or 4-dimensional fields, Maxwell fields and everything can actually arise from a 5-dimensional theory, or just it's a toy model that Kaluza-Klein was playing around with. That's what I'm trying to present. And then the 4-dimensional constants that we see in standard model. In standard model, we have a bunch of constants, right? Which are unfixed. Masses of electrons, charge of electrons, coupling constants, how the Higgs couples to the standard model fields. All of them are unfixed because we're putting them by hand. But this gives a hint that maybe they're not so arbitrary that we really think it is. Maybe they're coming from compactification of one or many extra dimensions. Because these extra dimensional ideas show that they, in principle, can come from one or more extra dimensional ingredients. Similar to gravity in 5 dimensions. So this is what was the selling point of Kaluza-Klein theories in the 20s. That program did not last long, but it was again revived when string theorists started studying it. So what happened is when we considered a gravity in 5 dimensions, you get a 4-dimensional theory of gravity plus Maxwell equations. So this is huge, right? You have a unification of gravity and electromagnetism coming just from 5-dimensional gravity. So a 4-dimensional observer would see gravity plus gauge fields. That's super nice. Yes. the four-dimensional, the four-dimensional, it will definitely form the five-dimensional. That's that the brain wall graph. Yes, people have considered these brain wall models where you have 5 dimension, where you have 4 dimensions stuck on the brain and blah, blah. Yeah, it's part of that. Very, yes, very good identification. Okay. So with this, I moved to string theory. Why string theory tries to answer those in one framework. Using just one framework, we have these ideas. And then we move to relativistic point particle. So point particle traces out a line. So we try to construct the action like ds, integral, and it's easy to check that it agrees. So I'm giving out the answer, or you should get m x dot square when you take this limit. So that shows because a free particle that we know from classical mechanics should have this, right? The action should contain this, which is just a kinetic term. That's what we know from classical mechanics, physics 111, physics 1000, I don't know, something like that. So from our basic courses, this is the kinetic energy of a free particle. So take this limit. I insist you work this out and you will get this. So similar to point particle, you can have strings. Why strings? I motivated this in a huge monologue last time. But why strings? Because it's when you trace out, okay, forget why strings. How strings? So it traces out a sheet, a paper in space-time. Like every point is, if you take a snapshot or a picture of this, every point is a string moving in space-time. With this, I said, since for the point particle, I took a random guess and it turned out to be correct. You can check. Okay, I should have said something. If you have a computer or anything, you can turn on David Tong's notes. I can keep referring to it. Maybe it will help. I was suggested by one of you to do that. So if you have David Tong's string theory notes, keep it open. I'll keep referring to that. Although I do not follow him completely, I can say in which section he says about this. Okay. Questions. So, relativistic point particle traces out a world line. String traces out a world sheet. Now we are done because it turns out to be correct, because previously for point particle, it was proportional to ds. For strings, obviously it traces out an area. Instead of a line, it should be proportional to the area. That's the action for strings. And it turns out this guess is correct. You can take our favorite tools to play around with, Lorentz invariance and yes. Sorry? You can play around with that as well. Very good. I forgot that. You can play around with that. And you can play around with this. This is my favorite tool always. It's always the case. I think when we build consistent theories, that's what we always should do. One thing. So if someone comes up to you and says, look, I have a quantum theory of gravity, which is better than anyone else. So what have you, for instance, been doing? To show them this. This is called known physics in known limits. General relativity boils down to classical mechanics in known limits. Quantum mechanics boils down to classical mechanics when you take exactly h bar to 0. Classical special relativity boils down to classical mechanics when you take very good, v much less than c. Known physics in known limits. It should be the mantra. Okay, moving on. So we had these strings, and then something more amazing happens. So we have this equation of the strings, which has a weird absurd square root, annoying. Yeah. Then what we do is try to construct the equation of motion and see what happens. Okay. we have the equation of motion. Turns out we can do much better. We can construct this another action which is very similar to this guy. And I've given this as a homework. You can try varying this action and you'll see you'll get the result. It's not too difficult because we are equipped with the machinery of Euler-Lagrange equations, right? You know, if you have a scalar field, play around with the scalar field first, then come to this. You should get this. Okay. And then we talked about how they're equivalent, but with one subtlety that this has its own equation. Yeah. With that, we say that the symmetry of Polyakov action, this Poincare invariance, of course, relativistic string, it should have Poincare invariance. Relativity should be built in. Parameterization invariance, physics independent of coordinate. That's, of course, that should make sense because I can use a coordinate, maybe, I don't know, Nusrat uses a different coordinate and we're dead. Physics should be there, but physics should be invariant under different coordinates. And then while invariance, this is something that we never saw. What is that? So it really means when you transform the metric. So what does metric describe? So metric is something like this. A metric describes how your physics or your geometry looks locally. So this transformation says you should exponentiate by this coordinate. Here coordinates are sigma. Or if you change your coordinate, let's say you're from here, you move to this weird coordinate or a metric that you rescale your geometry in a weird way, your physics is invariant. That's what while invariance is all about. We're rescaling the metric. And when I do this while transformation, my action that I wrote for the Polyakov action is invariant. That's weird. That's another weird thing going on. So with this symmetries at hand, we can simplify physics a lot. So you can just prove. So in the Polyakov action, there's only these two guys will transform the while transformation, right? Because you're just changing the metric, nothing else. So if you plug in this transformation, which should be not too difficult because you're just transforming the metric by this, the determinant will transform in the opposite way. So they have a cancellation. You can quickly check this. And then I think you will be more convinced that this is this while invariance. And this is the easiest thing to check. Just plug it in the Polyakov action. And then we can use symmetries to simplify our lives. And we arrive at this very simple equation, which is a theory of d scalar fields. Yeah, because this index mu can take now d values. And then we said, I promised that your life will be much simpler if you take these coordinates. And it turns out the equation for a relativistic string is just this simple equation with two variables acting on some function. That is something that we learned in calculus 2, calculus 1/2, HSC, BSc, or anything, right? So we can solve this. So this is done in, again, I forget referring to, in Tong's notes where I think in chapter 2, right? Anyone with chapter 2? Chapter 1? Chapter 2, chapter 2, chapter 1. The classical string. I'm in classicals. It's in chapter 1. Yeah. In chapter 1, just look at this. You're just solving a differential equation. It can be followed. If not, I'm around, just reach out to me and then we'll discuss one-to-one. So as pointed out last time by 3 of you, what could be the option for strings? It can be closed or it can be open. Open means it's stuck at something, maybe this wall, or closed means it comes back to the same point. Imposing these boundary conditions, and then we ended our discussion. Okay, I'll keep out from that. Any questions on that, on this summary? Any questions? Please feel free to ask me questions. Okay. I lose a fine comeback. Oh, one of my problems that I always do is to shorten things.
Ancak yediğinde bir crack socket. Yedikte tarihçilik yediğinde that's it.
With this one.
Can it was more about cups?
Yeah, similar to what I showed, you just consider one extra dimension. That's what their goal is, and study physics in the one extra dimension. In 5 dimensions, let's say, you could be 6 dimensions, where in 6 dimensions, you could take two of them to be two circles or something like that. That's the simplest setup we know. People have considered more complicated setup, of course. So by considering one extra dimension, that is 4 of the ones we see around us, and one dimension, we need to note that if extra dimensions exist, they're hidden from experiments because we don't see them. Either they're too weak to be observed in energy scales because we cannot go very low in the energy scales and very high in the energy scales. Either they're too weak to be observed or too energetic that we have not reached those scales. So what they did is 4 dimensions that we see around us, 3 dimensions of space, 1 dimension of time, and 1 extra dimension, that is that of a circle. And this gives rise to physics in 4 dimensions. Note that when we are trying to do physics, we should do it in 4 dimensions because we live in 4 dimensions. But the interesting part is that the extra dimension has an effect in your 4D theory. That is giving you your gauge field or your Maxwell tensor in 4 dimensions from the direct space. Yes.
Say all compact space bigger mistake.
I think we would have observed it, right? That's why the compact stuff.
Yeah, picture like
Very good. Yeah, people have done it. You can check the notes of Chris Pope. If you know a bit of differential forms, that is the most helpful one. If you don't, then maybe look into Fernando Quevedo's chapter 7 of supersymmetry and extra dimensions. Okay, let's get started. So with this, I will be very quick. So as I was saying, in QM, you had this oscillators. When you acted, let's say, what should I denote with? A dagger, you get new states, right? This is what we had. The analog in string theory turns out to be this alpha oscillators. Now, alpha takes values from, let's use this. Let's call this excited state or first excited state. Okay. Similar to QM, you have this analog where you act with this oscillators and get this excited state. So where I noticed the confusion where I runs from 0 to d minus 3, I think, in this case. I don't know. Yeah. You should have d minus 2 degrees of freedom. So I think one of you asked yesterday why d minus 2? Because you are doing a gauge fixing, right? Because remember I did something to simplify my life. That is, I choose a certain gauge so that my Polyakov action becomes, the equation of motion is simplified let's use to this. This means you're getting rid, when you do the quantum theory in full generality in chapter 3 of David Tong's note, you see that in the section called light cone quantization, in this, you'll see that you lose 2 degrees of freedom, or 2 degrees of freedom are fixed, where degrees of freedom means the options you have in your theory are reduced to by 2 because you fixed certain case. So that's why you have d minus 2 degrees of freedom. But that's not the story, complete story. It turns out these oscillators, unlike something we had in quantum mechanics, have this interesting property where the 0th mode gives you m squared. I am surely wrong with the notation or of David Tong, but you get the mass squared. What does it mean? We've seen this invariant mass, right? In, have you seen this? This part looks familiar a bit. General relativity, special relativity, special relativity. Right? What is it? Exactly. That's the invariant mass, right? This is weird. We never had those in ordinary quantum quantum mechanics. But since, okay, we are dealing with the relativistic theory, maybe this is expected. And it turns out that the first excited state, if you compute this, gives an expression for m squared, which is, let me write it like this. Now, this is super important because this is my punchline, probably. So I should not say the punchline before saying it's punchline, right? So this is probably my punchline. So Lorentz invariance forces this guy, the first excited state guy, to be 0. So when is it 0? When is this m squared 0? I'm trying to tell a story that when is this m squared 0?
He's 26.
When you choose, so what do we have? We compute, we go to the machinery of quantum strings, we quantize the strings, then we are done with business, we act on this vacuum of string theory, and then we get the mass squared. And this mass squared, which you have to trust me, comes out to be something like this. And Lorentz invariance tells us that this mass squared should be 0. When is this mass squared 0? D equals 26. That's sometimes called the critical dimension of bosonic strings.
Bosonic strings, what are these?
So yeah, I'll go back. What's the problem with bosonic strings? Yeah, I'll say what bosonic strings are. So what has happened? This has never happened to us in QFT. I'll give analogies with QFT because these things never arise in QFT. In QFT, you arbitrarily, by hand, set the dimension to be 4, right? Did we ever, in the quantum field theory class, did someone ever say that the dimension is fixed somehow? No. But this is something nice, even though this is absurd. I mean, what is 26? What do you mean 26? Are you, that's not a socially appropriate word, but what do you think? But this is a cool feature, even if that's absurd. Why cool? Because we never had them in QFT. You never had the dimensions fixed. So this fixes the space-time dimensions. Those who are a bit from the advanced audience, this does not necessarily mean you have a 26-dimensional theory. If someone knows conformal field theory, please reach out to me. I'll explain to you. But those of you don't, this actually means 26 dimensions. Okay. So what has happened? So our requirement of largest invariance fixed. Our requirement of largest invariance fixed the dimension of my theory, which we never saw in KIFT. Okay. But this has another problem. Few problems. As she pointed out, why am I calling it bosonic strings? Because what is Klein-Gordon equation? The equation of what is it? Is there fermion anywhere here? No, right? There's no fermion. The fermions have this weird psi bar business going on. The Dirac equation that I've tattooed here, that's not there, right? That's not there. The psi bar business is not going on here. So that is why I'm saying it's a bosonic strings. So the problem with this, apart from this, is that if you see this as a problem, is that one, no fermions. This is not correct. We do not live in a world there's no fermions. Otherwise, me, you, any one of us should not exist, right? So this is a problem of bosonic strings. But it turns out bosonic string theory is a good learning tool which teaches us what to do. There's another problem. Okay, I should have mentioned this here, but I'll come back to this. So if you look at the zeroth state, let's say I restore if you plug in 26, it's still a minus. What does it mean to have negative mass in a field theory sense? Anyone? Have we seen in Shadman Rai's lecture that the Higgs mechanism, that was he talking about an unstable minima? Okay, so maybe I can quickly motivate this. Usually when we do physics at the minima and try to see oscillations around that minima, because that gives rise to particles and the things we see. Small oscillations or deviations from your initial point of view or initial minima give rise to particles, dynamics, and so on. But if something is negative, it really means that you're expanding around a maxima. But if you expand around the maxima, it means you roll down and your minima or your stationary solution is not stable in that sense. So this is problematic. This is called the tachyon of bosonic strings, if you have heard about it. And one of our speakers of the main school solved the tachyon problem, which was one of the most annoying problems in bosonic string for the open strings, which is Ashok Sen solved it. But still, we do not have a solution for the closed strings. So that is still a problem. Tachyons are unstable, unphysical, unwanted optics. So lastly, I just wanted to mention the problems with bosonic strings. And then if you just have, again, compute these alphas on the zero states, on the vacuum, yesterday we saw this gave rise to few things. One, the first excited state gave rise to a metric on the more positive note. And it gave rise to something with two indices, but antisymmetric, which we call the B field, sometimes Karl-Bramond metric. And on this side, it gave rise to a scalar field. These are the wanted ingredients that we want in life, right? We want a metric. Forgetting that this is the case, which we should not forget. I'll come back to our unwanted things again. But we have a metric. So what just happened? We took a relativity strain, we quantized it, and we looked at the first excited state. Gravity pops out. That's weird, right? We did not impose gravity by hand, which we were doing for any other theory that you would get. Let's say if you take the Einstein-Hilbert action, try to quantize it, you're putting gravity by hand. Here, did any of you see I'm imposing gravity? No, I'm just doing special relativity, right? Special relativity, relativistic strain, quantized, gives you gravity. That's a positive takeaway from the more unwanted aspects of bosonic strings. Questions? Yeah, I should have said that. I remembered that I would say this. So, okay. So for QE, yeah, let's do ENM. For ENM, you had A mu, which is our gauge field. So once you're given a gauge field, what's the favorite thing that we do? We compute the field strength because that's what we write in the action. For here, let's not write bosonic strings because this is common. Or let's say here, P mu nu. Do I have charge here? Yeah. B mu nu would give rise to a 3-index. So if you know the anti-symmetrization, it's taking the similar stuff to this, but with one more index. It's similar to the electromagnetic field, but with one more index. This is now the reality we live in, for sure, because we don't see this guy. If this guy exists, we don't see it. But the positive takeaway is that you have metric gauge fields arising from this toy model setup and scalars. So gravity, gauge field, scalars arising from this. That is our positive takeaway from this toy model of bosonic strings. Okay, I'll skip lights and see what I get. So for until now, I discussed closed strings. Now comes another possibility, that is open strings. So what is that? So sigma and tau are my coordinates. Sigma is the coordinate on the string and tau is a time-like coordinate. Zero to pi. So this would give me my closed string. Something like this, blah, blah, blah. Okay. So let's see what changes, because we now have to impose the boundary conditions, because closed strings can end, right? So let me try to do this. These are some notations that I'm using. For this, I would ask everyone to go to Tong's chapter 4, open strings and D-branes or something. That's the name of the chapter. I'm just copying from him. Chapter 3, open string and D-branes, right? Okay. Open string and D-branes. So if you take the variation of the action, you get d tau. So if you remember that when we do the action principle, let's say tau I, tau f, you take all possible paths, but keep the endpoints fixed, right? That's what we do. let's say path integral quantization, like any possible path that you can take is possible with this from initial time t to final time f. Dx. So I took the variation of the x field, and it turns out that if you see the manipulations in Tong, it turns out there's some boundary conditions that used to cancel for the closed strings do not. So boundary contribution. That is, since the endpoints are not coming back to the same point, the cancellation in the integral does not happen. You can check this out just by plugging in. So what happens is that I can impose rules. Is it? I think it's expand. Wait. Tau f d tau x prime dx sigma equal to pi 0. This term does not generically vanish, right? You can see, you can work it out that at the endpoints, if the endpoints came back to the same, so this and this means if this is an definite integral, if it comes back to the same point, this is 0. If this was the same point as for the closed string, you would come back to the same point and you would have a cancellation of the two terms. Definite integral, right? Something minus something, GG. But that's not the case here because those 2 points are different. So this term we have to impose something because otherwise we would not get the equation of motion. But this term should be 0. There's 2 ways out. One, it means the endpoints are fixed. That is x, the variation at the endpoints, like the motion in x at this point, 0 and pi, are fixed. So it does not move. So you can impose the boundary condition that del x mu equal to 0 at sigma equal to 0 and pi. If it is 0 at both points, that's a cancellation. This term vanishes. That's okay. And that's something we see from classical strings as well. Classical strings can end on something, right? If you have a string, take it, can end on the wall or something. This gives rise to something called D-branes. And those of you who have done a bit of waves and differential equations, this is called Dirichlet boundary conditions. And there is another possibility, which is called the Neumann boundary condition, which you take x prime to 0. This is another possibility. It means that the string can slide around. It means that the motion along the x direction, it can slide around, but the derivative of that is 0. It really means this. Maybe I'm not being super clear. Should I use a different? Let's not. 0 and pi. So 2 possibilities. One, your endpoints are fixed at certain points. It cannot move around. Another case is that your endpoints are not fixed, but it's confined to a plane. I can make this a bit more intuitive in the sense that if you think of a plane, so up there, I imposed Dirichlet boundary condition. This is called Neumann boundary condition. It really means, can the string go up? No, right? You're confining it to this plane, like to this table in front of you. You're confining it. It can move up. That not moving up is called a Dirichlet boundary condition. If you look at the table in front of you, if you take a string, stick it inside the table, it cannot move out. That's the Dirichlet boundary condition. Sorry? এই যে দেখো, so this integral, is it clear why this should be 0? হ্যাঁ, so ওই ডিরেকশনে ভ্যারি করবে না। তুমি যদি উপরে যেতে চাও, it won't let you. Yeah. Yeah. So it cannot move up. I'm using that direction, imposing Dirichlet boundary condition in this direction, Dirichlet Norman boundary condition in this direction.
Wait, this biggest ink.
Yeah. Yeah. So this plane that it's confined to, it's an extended object, for sure has more dimensions than the dimension of the string, because otherwise it attach kora possible hoto na. At least one more dimension, maybe 2, maybe 3, maybe 4. It depends on the setup. We have to look, but it's confined to a plane. We call this extended object branes, and this gives rise to something called D branes, where D is just this. How lost on a scale of 1 to 10 are we? 11? 26. That's that. I understand. I tried to improvise from last time because adding equations would make things more troublesome. So what I tried to do is try to intuitively argue why this should be the case. So a lot of the argument will make more sense if you look at the math in Tong's notes. And I believe the relativistic string, just from the relativistic string perspective, is something that with all of us can do with just basic understanding of classical mechanics and special relativity. So go into the notes of David Tong, look at the relativistic string. If you know a bit of quantum mechanics, what is the thing that we really can do is impose canonical commutation relations. That's the baby thing we learned around 120 years ago or something. That's what we have been doing for the last 100 years or something. So impose those conditions, act on states with ladder operators, and you're done. You get these objects. Okay. Last point before think time, is it? Mm-hmm. Okay. I'm good on time, like very good on time. Okay. So it turns out you can now do the same magic that we did for the closed strings that we can do now here, which is act on states with oscillators. It turns out if you are confined, if an open string is confined to the brane, if you act with the oscillator. Yeah. So, okay. So think about a string. It has to, we impose the condition that it ends somewhere. The dimension of that object should be more than the dimension of the string, right? Otherwise, otherwise it will be a closed string, right? If it does not end, if it ends on a string, it's a closed string. It has to have one more dimension than the string. So what is the maximum one more dimension? It's a sheet, like this paper. This could be the two brane because 2 dimensions. So a string can end here. So these extended objects we are calling D branes. because of the Dirichlet boundary condition, and brains because they are extended objects that come from the word membranes. So one, so we are calling this membrane. So a D2 brain would be the sheet of paper. D3 brain would be our 3D world, like a cube maybe. Yeah, open strings end. Yeah, very good. Yeah. Not not necessary. No, it depends. There's a subtlety in there. Yeah, very good point. They're inside the whole space. It can be a submanifold. Yeah, very good. Yeah, it can be a submanifold, but it's not it's not a whole manifold, right? Let's say a D2 brain living inside. Let's say you. Okay, bad example. You living in a 5-dimensional world, or your space around this could be a sub-manifold, not the whole manifold, right? Because your dimensionality is less than the dimensionality of the total space, right? Maybe that's clear. Yeah. D1 brains have this other special interpretations. They're there, but they have another interpretations, but they don't have. Yeah, it's called F1 strings for some weird reason. But yeah, okay. So now we can do the oscillator business. That is, we can act on the vacuum with this. Oh, yeah. I should have mentioned this. A DP brain is a p-dimensional brain. For example, a D2 brain would be a sheet of paper. A D0 brain would be just a particle. Oh, okay. Zero brain would be a particle. One brain would be a string. Two brain would be three brain, maybe a cube or something, a three-dimensional. Yeah. And then it could be more exotic objects like, yeah, it's hard to imagine from a 3D, 4D person perspective. So if you act on oscillators on this brain, that is quantum mechanical oscillators, you get something super interesting. That is, spin one particle lives on the brain. So what is the spin one particle that we know? Sorry? A bit more specific boson? Sorry? Photons. Yes, yes. Yeah, bosons, but photons. So it turns out it has this photons in it. So this toy model that we are studying is giving us hints that it could hide features of the universe we live in. Metric, gauge field, photon-like fields. Tom calls this a world of light. This section I remember, just remembered. He calls this world of light because photon, light. So it was a nice one. Yeah. And it turns out you can have the non-abelian gauge theory that we see from the standard model with these brains that you have stacked them up, like it gives rise to. So a photon has what gauge symmetry? U1, right? U1 gauge symmetry. If you have n of them, this U1 n times is enhanced to SUN. So this is interesting. What just happened? We have the metric gauge fields and SUN gauge theories popping out just by stacking up brainings. So ingredients of the world we live in are there in these setups, this toy model of bosonic strings. Things will get much better when we move to more sophisticated string theory, which are called superstrings, which has the fermions and things like that, and no problems of the bosonic strings. Lastly, before I think I'll what how much time do I have, Samit? Huh? 50. Okay. Yeah, I'll end this session with one thing, and then the last session will be very short. So should I? Okay, a suggestion. Should I finish together? Like I would need 40 minutes more. Then I'm done. It's okay. Or should I give a break and then a break? Yeah. Okay. Okay. So lastly, I'll end the session with something called TBI action. So these brains should have dynamics, right? Things in gravity move, as we saw. This should have a dynamics. So let's go back to our Nambu-Goto action. So no, let's start from a bit more earlier. Point particle. I'm forgetting the constants, so let's give this. For strings, or since we have become more sophisticated, we write Nambu-Goto NG. So dA, it traces out an area, particle traces out a world line. So brains, what would it trace out? Volumes, right? It will trace out a bit higher one dimensional or many dimensional mode. So this will trace out a D of, let's say, world volume, or D of V. Let's use this. Let's use a bit more sophisticated word. So it turns out, similar to Nambu-Goto action that we saw, it's the DP brain action, where now the tension is generalized to a tension of the p-dimensional object. For the string, we had a tension T. Now it's extended to more extra dimensions of gamma that we saw before. Similar, but with more indices flying around. Exactly the same. With this, there's one thing ingredient missing. The light guy, right? As I wrote the oscillators, the right guy was missing. Light guy was missing. The photon, right? The gauge field was missing. So light guy and the right guy should be incorporated with the action. And we'll see after the break that, okay, we won't see by a method called T-duality, which I will briefly discuss before I end the session. You get the action of a brain called the DBI. Any guesses what D stands for? Okay, Dirishte, one Dirishte. Huh? Both, both of you. Anyone but both of you. Anyone else? What does this stand for? And this will be a history lesson for you. No phones. Did you guys hear?
I didn't.
It's Dirac. Dirac born in field. It's weird, right? Dirac born in field. That's what I invite you to look at. What is the spelling of infill? This? Okay. Yeah. So with this, we have few things before I wrap up this. And I will go the next session without notes. So more mistakes. So what happened? We started with a relativistic string, tried to quantize it, look at the states, excited states. We get a bunch of interesting things, metric, and so on. And then what happened? We moved on to the next session where we imposed boundary conditions on on our strings. And that gave rise to brains. brains are super interesting because they have gauge field or light inbuilt in them. It turns out if you stack them up, like if you put coincident grades together, you have a SUM gauge theory or an ingredient which you see in the theory of standard model or the universe we live in. And one second, let me show. Yeah, no problem. And then we look into the dynamics of these objects, extended objects. And the dynamics of this extended object has physics which you can describe by an action which is very similar to our string action, but with more dimensions and degrees. This is a wrap up of what we did. And yeah, maybe questions, then I'll finish shipping a few more things.
If you want a symmetrical periodic characteristic or SUN, but SUN can one can
You have n gauge symmetries. You can actually show this argument in Tom. Oh, special.
enter. এখানে SU1 cross to SU1 করে হচ্ছে
It can take the enhancement of gauge symmetry, right? That happens because of us. If you look at the mass squared of this is a bit out of the scope. If you see, look at Tong's notes, just one section, a one-page note. He explained why you have an SUN enhancement. Just look into that. Now, a post arbitrary dimensions. These are I'm still in 10 dimensions. Sorry, still in 26 dimensions. I've not simplified my life yet. And with no fermions, with an unphysical vacuum and all of those ugly parts. But since we are all positive person, we take the positive lessons and try to learn from the negative lessons. Or, yeah. So this problem, how much time do I have left? Okay. So let me say a few things, then I'll end this session. Few positive notes. One, this toy model has a metric plus gauge fields. And I'm saying with the brains as well, you have those gauge fields. And okay, charge is dead of the Okay, I'll just say it out now. Ahmed, do you have your pen? Yeah. This is this the old one?
one. Reading.
Lun. Okay. And dimensionality is fixed. I'll still give it a positive point because these are lessons of quantum gravity, right? Because we never had this in quantum field theory. So when we try, as we see, it's already too difficult to go beyond the standard model because a framework that unifies general relativity with standard model is absent and it's super difficult. So any lesson we try to get from a theory of quantum gravity will be a lesson, general lesson. So this is a list as a positive because the dimensionality is fixed. Now, what improves? So how did we fix the dimensionality of bosonic strings? Any ideas? Like how did we say it's 26 and not? Yes. And what is the condition that fixes it to be Lorentz invariance, right? So this is important for your theory. Our theory should be Lorentz invariance. The requirement of Lorentz invariance fixes the dimensionality. That is what it fixed, the dimensionality. So let me write this out. Lorentz invariance. So this is a very beautiful argument. Those of you who have done a bit of group theory, check out the notes of Tong, where he gives a beautiful argument why, how, and why the dimensionality of bosonic strings become 26. So why it should be massless. Every argument is there. And oh, wait, you guys have seen it last class. The SO8, the little group should be SO8. So that is a requirement by Lorentz invariance. And yeah, okay. Sorry? No, he was talking about that the head. Yeah, but that's what it fixes it. The group theory arguments combined with Lorentz invariance, but actually the underlying arguments is Lorentz invariance. Okay, so what improves? What improves is that if you consider fermions in the worldsheet, which is a requirement, look at it, then dimension becomes 10 and something more amazing happens. So in quantum field theory, how many quantum field theory can you write? If you're given just the framework of quantum field theory, no experimental inputs. Yeah. Anyone? You two can answer if you want now. Both of you can answer now if you want. How many quantum field theories can I write if you have 0 experimental inputs? Yeah, I don't. Yeah, but you know the answer. Let's see if anyone gets it. You're right, of course. How much? Infinite, right? Infinite number of possible quantum field theories that I can write. Scalars is without experimental input, whatever the world I like exists in quantum field theory. But it does not turn out to be the case in a theory of quantum gravity. So you have, okay, the I should mention this, that 1A, okay, yeah, maybe I should just write here. The requirements of having fermions in the worldsheet makes the worldsheet supersymmetric. That is, the fermions have a transformation that relates to the boson. It enforces this symmetry. And on top of that, you're left with 5 consistent theories, just 5. And each of them are related to each other. So I'll write my favorite one first, followed by the second favorite one, followed by the third favorite one, followed by the fifth favorite one, but I'm writing it for consistency. These have inherent meanings. These are the gauge groups. And my least favorite one, and I think everyone's least favorite. But that guy is still cool. Okay. So these are related by something called T-duality. So you have 5 consistent theories pop out, and all of them are related by this web of dualities, the picture that I should have shown everyone. So so you have 5 theories popping out, all of them are related, which we never had in quantum field theory. I'm giving references to quantum field theory because we should take lessons from the things we know. When we tried building quantum field theory, we took lessons from quantum mechanics. But this is something nice. Each of them are related to each other in some weird ways. You'll see some symmetry relates them. So this is nice. So ultimately, it means that a solution in one of them has a solution in the other, and so on. That's what a duality means, right? A duality symmetry. That is, let's say if me and let's give a guy, Orko are dual to each other, then a solution of mine is a solution of Orko as well. So that's what dualities are telling you about, that your solutions are fixed. So you have 5 theories that which pops out, uh, and they are related to each other by this web of dualities. Just search it up, web of string dualities or string dualities. You see a beautiful picture, and all of them are related to each other. And it's all of them are the only possible consistent theories that you have. And it has no weird business such as tachyons. And it has all of the nice ingredients that I listed of the problems of quantum gravity inbuilt. What you have to do, take your pen and paper, study them, and try to do physics with them. That has all beauties inbuilt in it. It might not be the theory of quantum gravity. Of course, there's an if, because without experimental input, without seeing physics experimentally, the ideas will not be the universe we live in. But it certainly teaches us about how a quantum theory of gravity should behave. Yeah. So, what has happened? So, I told ourselves that we have superstrings. Let's use this superstring theory, a theory in 10 dimensions with no bad features of the bosonic strings. Okay. So let's start with a few disconnected concepts. So if you have a theory in 10 dimensions, what you do is, let's use, this is not sim equal to, it's like I'm writing the product manifold. M4 cross X6, where X can be any 6-dimensional manifold. For our vanilla case, where you had 5 dimension, one of them was the circle. This could be 6 circles in chapter. Is it here? Okay. So we have 6 circles. So this could be that. This could be other objects. So those of you who know a torus, it could be T6. It could be, or a more fancier one we'll see in the last lecture of geometry and topology, called Calabi-Yau manifolds, which are a class of complex manifolds. So in Jim's first lectures, we saw real manifolds. That is, we'll have a complex manifold here. Could be the case. So it could be any 6-dimensional manifold we see. And this M4 is our world. So it could be Minkowski, which is, you should know, 0, which is a flat, or ADS, where lambda is the cosmological constant, or DS. But we know that we live in a de Sitter world. What does a de Sitter world mean? We live in a world where our universe is expanded, right? Not just expanding, the expansion is accelerating. It's an accelerated expansion that when we look out at the farthest point in the sky, or when we look out far using our telescopes, we see that the universe is expanding at an accelerated rate. What does it mean? The farthest point in the sky are moving. Let's say if you have 2 points in the sky, let's say at distance D1 and D2, D2 is moving which is farther from, let's say, me, it's moving away faster. D2 is moving away faster from me compared to D1 because you have an accelerated expansion. Okay. Okay. So a theory in 10 dimensions. So what are the field contents of I go by? Okay, let's me do this in my mind. And then remind me to talk about T-duality. And I'll finish my lectures there. So what is this? So what should be here for QFT? We had D4X. What will I have here? What will I have here? Yes, but the totals is D10. Let's say I'm in 10 dimensions now. We'll have a 10. But as Taki pointed out, if you're doing a compactification, this is called a compactification, you'll have D6X, right? D6Y. Let's label them by Y. But yeah. So let's say we are in a 10-dimensional theory. What are the constituents? Our metric is always there. It's a gravitational theory. It's always there. Then there's the curvature in 10 dimensions, which is the Ricci scalar, which comes, remember our metric that we showed and I celebrated and I made a big fuss about it, that you have the metric, guys. Gave you guys a wake-up call that just the relativistic string quantization metric pops out. This is the metric in 10 dimensions. And then I made another big fuss about another gauge field being there. Yay, gauge field. But I have to write them in the action. I forget it's 3 factorial times 2, right? Yeah. Okay, I should be using better indices. Where M and N start from 0 to 9, 10 dimensions. Plus, I have few more things. One more thing that I had. Yeah, I forgot the how to write it, like d phi. Let's write it d phi square. Let's use this. So numbers, I'll get it wrong by huge margin. So I'll explain this constant later, but what are the fields that I have? Then I have a bunch of gauge fields, FP squared. I'll explain this notation now, but before that, this comes from another. So remember, we imposed the boundary condition for just the bosons. We impose the boundary conditions for the bosons, but there's also the boundary condition for the fermions. The bosonic guys give rise to this. The fermionic guys, imposing boundary conditions in superstrings, give rise to a bunch of other scalar fields. Sorry, gauge fields. So what is 2 kappa 10 squared? Before that, I should explain this. It is the only parameter in the theory where alpha prime to the 4th, alpha prime is LS squared. The only free parameter in the theory. That is the string length. So for us, for the main school lectures, at least for the cosmology part, all you need is written in this page. 1, you need the field content of your theory, as we all know and as we all should see in quantum field theory. If you know the field content, you're in business. We gave all of those things as a backup. How these things came was a motivation or showing that how to arrive at this. But all of this here, that is compactification, the action of, let's say, type 2b superstring theory, is what's all you need to understand physics there. So these will give rise to particles like standard model like particles. This will give rise to the inflaton. This will give rise, inflaton is the candidate which causes the accelerated expansion of the early universe. This will give rise to dark matter candidates. This will give rise to anything that you see in the standard model and you do not see in the standard model. So which are the ingredients that you need for the main school? It's all on this page. And for type 2b, it is P equals odd. You have the odd number of them. So you have F1, you have F3, so which is DA0, which is DA2, F5, which is D. Okay. This is not a standard notation. I should use standard notations. Oh, right. Sorry. Right. Right. Yep. Okay. So Jimba introduced exterior derivative, right? So let's see, probably this. So what does this mean? F3 would be if mu nu rho. Let's give it a try with wrong indices. Surely I'm gonna mess up. Uh, let's see. Bro, mu nu. I think I'm right. This is the field strength of the two index gauge field. So similar would be this. For example, for this, it would be. So we learned about the exterior derivative in the lectures on geometry and topology, did we? We did, right? I remember he talked about Leibniz rule of this exterior derivative. It takes you from, uh, let's say you have, it take, let's say, did we learn about differential forms in those lectures? Okay, okay, okay. I'll not use forms notation. I'll just expand it out in terms of the indices we know. Okay. So in terms of the indices we know, it looks like this. So these are field strengths, and the D's, forget about them. We don't like them. They are just partial derivatives in this sense. So it's the same one we had for the Maxwell field, but with one more index. One more index means you run over more things in the partial derivative. You run over more combination of things. That's what's happening. So this is the field content of type 2b string theory. So that's what is the end of the story in type 2b string theory, at least at the level of the 10D action. Now you do business with it. What are the business that you can do? Let's say, let's see. Should I talk about business first, then T-duality? Yeah. Okay. So let's think of an example, what we can do with this. Before that, so have we seen how particles couple to gauge fields or electromagnetism where we had a whirl line, Maxwell coupling to a whirl line? Did we see this in ED, classical ED? Did we see this ever? So a particle being charged under the Maxwell field, or a particle charged under your, what is it called? Electric field. You've seen? Should read. Okay. I think you did. Yeah. Particle charged under a gauge field. Okay. No, not in any courses. not in this school, maybe in electrodynamics. Have we seen this? No, right? Okay. Okay. This is an ED lesson that particles couple to the whirl line of your gauge field. And you can write the coupling as something like this. So a particle
Silver possibly. So
I think you at least maybe a bit rusty, you're a bit rusty on the end, but you should have seen somewhere maybe. Okay, if not, just look the particles coupled to each. Just Google it or ask any AI to explain it to you what particles. I'm sure you would understand it right away. So of course, if particles can couple to it, our theory contain extra dimensional objects. So a string can couple to an object with two indices, right? A brain can couple to, let's say, a D2 brain and couple to an object with. So one index object here couples to an object here with 0 dimensions. Here you have one-dimensional object coupling to two index guys. Two-dimensional object couples to, yeah, three index guys. So brains can couple to this weird extra indexed gauged fields, and and it can be charged under it in the same way a particle is charged under electric fields or magnetic fields, of course, because there's of course electric and magnetic duality. So a charged under electric field or gauge fields is what it means, and then you extend the ideas. Yeah.
yeah. So T2 the clear yang আপনার এই magnetic field মানে electric field is to under the এটাকে explain করব
Not in the sense probably you're thinking, but yes, you are right if you think that these guys are changed under T duality. Yes, you're right in that, but
that's
not in that. But yes, of course, T duality would fix this or would change this. With this, in the same way, I advise you to look at after you are done arriving at the effective action, what is it called? Beginner's lecture on flux compactification. So there's this section. Can you open it and tell me which section is it? By this guy called Thomas Van Riet, where so if you have the gauge field, you can construct the equation of motion, right? We've seen this in the QFT classes. If you have a gauge field, if you have a field strength, do the variational calculus, Euler-Lagrange, whatever you want, arrive at the equation of motion. So the same thing can be done for, of course, in principle, if you have an equation of motion for this guy. What is the equation of motion for this guy? What is the equation of motion for this guy? I saw one answer. That's correct, probably. Can you say it out loud? Exactly. The variation of this guy would give you the Einstein equations. So you have Einstein equation popping out from just variation of this action with respect to the metric. similar to what you had, oh, wrong indices, similar to what you had for Einstein-Hilbert. So I advise you to look at page 25 to 29 of this note. So after you're okay with arriving at the action of type 2B string theory, which you can do from Tong's notes, and after you're done arriving at that, because, or you can just accept that, okay, there's this action, we are given action free of cost at QFT courses, in QFT courses. So I give you this action free of cost. Now you do physics with it. What do? You can calculate the equation of motion, which I advise you to do. If you know a bit of differential forms notation, try to do it from here. Or if not, just take by hand variation. Trust me, the answers with the person doing differential forms, without differential forms, they'll match. It doesn't matter which method you choose. So try this out. If not, just reach out to me. We'll have a chat. And lastly, I'll talk about something called T duality. Okay. So let's come back to our M10, where I do M9 plus my favorite example. What is my favorite example? A circle of radius, again R. So we saw, or we got a glimpse of how to calculate this quantity called M squared, right? Which is the invariant mass. So when you do this calculation, this comes out. We know this, right? This is due to the momentum in the extra dimensions. But this is from the classical, or this is from the particle perspective, right? When I was talking about this, when I was talking about this guy, this was just a particle field theory in 5 dimensions, and you consider one compact dimension, extra dimension, that gives you a massive field, and that this is what you are getting. But will strings have something more to say about this? Because particles, what can a string do in a compact space? In a compact space, what can a string do? Huh? Yes, let's see. You know the answer, but let's ask someone else. You know the answer. Let's ask someone else. Anyone else? Yes, strings can, if you take a string, it can wrap around this circle, right? And how will the wrapping be? What would it contribute to the energy? It will be proportional to exactly how many times it wraps. And then let's call it, Strong calls it M squared. No, this is super confusing. Let's call it W square. It winds around the compact dimension. What else can we say? Should be something more. So the wrapping will depend on the tension. Think about classical mechanics. If I wrap something, it depends. Sorry? No, tension. If I'm wrapping something, there should be a tension, right? Like একটা string এর কিন্তু it has a tension. If you wrap something up, it will be proportional to the tension times the number of time it wraps. So this turns out to be over this constant that we see. Let's not do it. Let's not write those constants. But the string length shows up in this. So I invite you to try it out. Plus those oscillators that I always talk about. So what does it mean on this sense? So you have strings in extra dimension. When you compactify one dimension, that is when you consider one compact extra dimension, which is that of a circle, something interesting happens. A 9-dimensional observer would see that the mass square looks like this. Okay, so what? But this places restrictions on the 9-dimensional observer. Because unlike the point particle case, if I shift this, is my mass invariant? Is my m square invariant? Okay, so this is weird, right? If I do this transformation, m square is unchanged. So 9-dimensional observer would have a hard time figuring out if they live on a universe where they have one extra dimension whose radius is r or 1 over r. Right? So what does it say? String theory, or in this case, type 2b string theory. Let's use string theory on a circle of radius r and 1 over r are the same. So this is weird. So we have a notion of a breakdown of geometry in some sense. We are not being able to perceive if we live in r or 1 over r. Sorry? Yeah, but you have to choose the units because you're talking about m Planck scale. In Planck units, if you have 1 m Planck, units are correct. That's called the T dual radius. Yeah, that's very good. So what is happening? So there's a notion of breakdown of geometry in some sense, right? Yes.
There's some special habit when the take of the streets was pay the
It just winds, right? You just wind around the sun. Just if you're thinking about how many times, once. Just then winding number is no, it just winds around that circle. But yeah, very good. So this is interesting, and this has a lesson that the notion of geometry is not being very relevant here. So this relates to one of our ideas, which we have, is that gravity might actually be an emergent phenomena, that geometry emerges at some scale. So if you just saying the buzzword so that you can look this up. Emergence, just search it, look it up, emergence of gravity. So that the 4-dimensional Einstein equations that we see emerges from something, or the 4-dimensional geometry that we see emerges from something more fundamental. And lastly, you can. I think I should give you this as a homework. Go home, take the type 2b action, just because if you just vary the action, you'll see that you get the Einstein equation. for EQI, the laws of gravity. Yes, as a skill like you should can be right progressive. I mean, yeah, in string theory, it's obviously the case that you get the Einstein equations full on. I think you're talking about the papers from 2009-10 on by Eric. Yeah, for Linder. Could be. I'm not. I don't remember the dates, but I remember reading about them. Yeah, some thermodynamic ideas, but I don't think that gained much traction. With, yeah, it's probably died out. Yeah, nice, very nice. Yeah. But like Eduardo yesterday, also I said that it also needs BN on this week. Yeah, I was gonna say that that's my next slide. Yeah, nice, very nice. So it turns out this is the duality that I was talking about on S1. If you match the spectrum of particles, they match exactly. So that is how two string theories are related by something called T-duality. So what one does is takes this action, as she pointed out, that you have, in this case, you have P odd, the field strengths are changed. That's what she was getting at. Then you are in the type 2A, you have P even. The field strength gets changed to even ones, and the spectrum matches in the lower dimensions. That is, in 9 dimension, the spectrum of states are the same. Maybe, yeah, that would have been better put. So a spectrum of states in 9 dimensions, they match. So we say that the two theories are T-dual to each other. That is, they have a duality relationship that relates the two of them. So this duality has been the forefront of study for the last 30, 40 years. We have been looking into solutions and trying to understand both sides of the duality better. And this is an interesting phenomenon because this is something we never had again in quantum field theory, like these kind of dualities. String theory also has this duality called strong-weak duality, or where you have we take the coupling constant. There's a coupling constant that emerges in lower dimensions, which we call GS. If you take GS to infinity, or you take 1 over GS, or GS to 0 and GS to infinity, they give you two different branches of theories. So one of the leading works on dualities was done by one of our speakers again. So Sen has done foundational works on dualities, and at times people were actually thinking if string theory actually was a worthy thing to do. Then the dualities revolution came in, spearheaded by Sen and others, and it really brought string theory into the picture. So please, if you're attending the main school, please keep asking Sen about this duality. Ask about T duality, ask about the S duality, or other things, other aspects of dualities, and he would give you like a brilliant explanation on this front. So with this, I'll end my session, and maybe you can add. Like is the small pesca. Already notes uptick. Nah. So the reference for the comment that Orno made is look into supersymmetry and extra dimensions. Extra dimensions. This is a lecture note. You can just pick up chapter 7, I think. This is a note by another one of our speakers. He has amazing lectures on supersymmetry on the internet, given at Cambridge. You can look them up and you can see the comment that Arno made, that the electromagnetic duality and its manifestation in higher dimensions. Yeah. So with that, I think I should stop. I've already fried your heads. So